Okay, let's start. Good afternoon. So this week is our final week regarding dimension theory. I mean, probably not, based on what I think we should cover, but still, at least officially it's our last week. So I want to do two things this week. First of all, I mean, today I want to discuss a little bit this heuristic for the Hutchinson formula, or Moran-Hutchinson formula for Minkowski dimension. Give some justification as to why this dimension, Minkowski dimension of the attractor of an iterated function system, which is sufficiently nice, should be the same as the upper similarity dimension. And then we're going to start talking about Hausdorff dimension. Initially, I was thinking to leave the measure theory sort of like minimal and then start discussing it next week, because we're going to need measures to discuss invariant measures and stuff. And sort of directly, or switch over to Hausdorff dimension as fast as possible. But then on second thought, I thought maybe it would be better to discuss a little bit the background of measure theory before sort of switching over to Minkowski dimension, partially because many of you are sort of looking into formulas that are somewhat related to certain ideas that come from measure theory. So I think it would be illuminating if you do it that way. Okay, so heuristic for the Moran-Hutchinson formula for Minkowski dimension. Okay, so we have a BIFS. As usual, we have a complete metric space X and finitely many contractions, and I put them into a set. And let's say that it has this unique attractor, A sub W. Recall that it's a compact non-empty subset of your ambient space X. The idea is that if your iterated function system is nice, typically there should be something like, each contraction here is in fact a similitude. That is to say, or similarity transformation is another word. Similitude. So far we were looking into something like this: Ci dx comma y for any x and y, and Ci we want it to be less than 1. For similitude, we want this to be equal. So the contraction rate is constant throughout the space. And probably something like an open set condition. For this heuristic, really what we're going to look at is totally disconnected. Which means that, recall, the images of any two contractions, I want them to be disjoint. Empty, so for I not equal to j. So this basically means nice. This is what I mean. And later on, we're going to sort of study these in a more precise manner and really give a more rigorous proof of some version of this equality. Okay, so we go back to this heuristic the first heuristic for the Minkowski dimension. So recall the first heuristic. So it should be something like number of cells times the scale to the dimension equals a constant, right? So if I were to just try to remember this, right? If I had the interval, I could cover it using n smaller intervals of radius or diameter 1 over n. So n times 1 over n, of course, to the 1 it should be, equals, in this case it's going to be 1. So epsilon here is 1 over n, and n is n sub epsilon number. okay? And n sub epsilon is n here. So based on this, we should have something like this then. The epsilon covering number, let's say, let's use the standard definition that we use in this class. The epsilon covering number of the attractor times epsilon to the Minkowski dimension, I'm just going to denote it by d, equals a constant. In this case, it's not necessarily going to be be 1, but it's going to be some constant in epsilon. So let's call it c. Okay? In other words, this epsilon covering number of the attractor should be c times e to the minus d, or epsilon to the minus d. This is my heuristic. Any questions about this? This we did last week, but I just wanted to reiterate. Yes?
So this is not a question pertaining to this, but specifically for the Eversing polarity dimension. Since I haven't looked at it in a while, what was the significance of having it be in the interval of 0 to capital N?
I mean, it just happens to be like that. Like you have n numbers that are between 0 and 1, and you look at this left-hand side function. Well, it turns out that this function has the following graph. It starts at n, right? Because if I were to plug in t equals 0, this would just be 1, and I'm adding 1 n times to itself. And then this is a differentiable function with derivative strictly less than 0, which means that it's strictly decreasing. And in fact, when you take the limit as t goes to infinity of this expression, it goes to 0. Which means that this left-hand side, as a function of t, looks like this. That's the significance. And ultimately, that means that there's a unique t value such that the height is 1.
Interesting. Okay, thank you.
Okay, yeah, this is just simple single variable calculus. Any other questions? And of course, in order for this to make sense, let's just assume we don't have this trivial case, namely that each of these, let's assume, each of these contractions are in fact non-constant. This is also implied by this actually, but nevertheless. And of course, if each of them is a constant, then that means that the attractor is a finite set and everything. It's not, you don't need any of these formulas ultimately for that. Okay, so I want to use this. And I want to use the niceness properties. So first of all, let me just delete this. I want two things. First, I want to relate the epsilon covering number of A, or the attractor, to the totality of the epsilon covering numbers of each of the pieces. Because recall that by definition, the attractor of W is a fixed point of the Hutchinson operator associated to the iterated function system. Which means that this is the union of all the images. Now first, let's try to understand the epsilon covering number of one of these images. You should think of it like this, right? So if this whole thing is my attractor, it has probably holes and stuff. And let's say one of the functions is wi. Well, it's going to be a smaller piece of it. And it's going to be sort of basically the same shape. It's just going to be a scaled version. So let's say this is a sub w, and let's say this is wi a sub w. which means that this number is equal to, so let's write it like this. So here, of course, Ci is supposed to be the Lipschitz constant. Let me just use that as an abbreviation. Ci times epsilon of this. Why is this? Well, because in order to get this epsilon covering number, recall that I just take a bunch of sets of diameter at most epsilon, such that the union is AW. Well, if I were to take each and every single one of those and apply WI, now their diameters is going to be exactly this number. We see this number is strictly less than this number, the epsilon, and Ci times epsilon. So Ci times epsilon is going to be strictly less than epsilon, and this number should be exactly the same as this number. Any questions about this? Because I'm just taking a bunch of balls of radius epsilon here, and I'm applying Wi to each and every single one of them, and I'm saying ultimately I should get back balls again. This is part of this niceness assumptions. So that's one. And then the second thing is that, again, by niceness, for epsilon small enough, balls that I use to cover one image should have no interference with balls that I use to cover another side. That is to say, so there's an epsilon such that if I is not the same thing as j, then two images are apart from each other. That is to say, their distance in Hausdorff distance, or Pompey Hausdorff distance, is bounded from below by epsilon 0. So, if epsilon is small enough relative to this separation constant, then because of this, I should have something like this. The total number of balls of radius epsilon that I use to cover A sub W, the attractor, should be this sum. That is to say, if I were to look at the epsilon covering number of each of these pieces and add them up, I'm not overcounting to get this. But then, if this is true, so I want an epsilon here, as you see, well, that means that I need to multiply this or divide this by Ci. So that means that this is equal to epsilon divided by Ci covering number of A sub W. Now, based on my heuristic, you see, this piece is nothing but C times epsilon to the minus D. And I can plug it in here as well. So this is C times epsilon to the minus D. This is equal to this. This is equal to this, which is equal to this. But then each of these summands themselves are equal to this. So same number. But you see the epsilon, the new epsilon number is something else. So epsilon divided by Ci to the minus D. Now here I have some factors that I can pull out. So this is C epsilon to the minus D. And then as you see, the sum of Ci to the D's. So which is exactly the upper similarity dimension. So, okay. So you see we were able to show, or at least heuristically argued, that c times epsilon to the minus t for any epsilon should be equal to this thing. Well, the only way that can happen is that this value is equal to 1. That is to say, because we had started with d equals the Minkowski dimension is also the upper similarity dimension. That's the heuristic. Okay. So from this, well, let me not write it. Any questions about this? At least this should sort of give you some idea as to why this Moran-Hutchinson formula is not saying anything very bizarre. It's like if you were to try to attach a certain number as a dimension to this attractor, it should be that number, basically. And of course, the real problem really happens when you start to sort of move these niceness properties a little bit and like try to relax them a little bit. So for instance, if the attractor is not totally disconnected, we don't have this simplifying assumption, and then discounting is, even though ultimately it is true, it's not as simple as this, for instance. We're going to study that later once we figure out Hausdorff dimension. First, I want to give the definition of Hausdorff dimension and discuss some of the basic properties, and then go into the proof. Questions? Comments? So this is one of the important ideas in this class, so you should be comfortable with this. Okay. So that's that. Let's now do some measure theory. Then we're going to switch over to Hausdorff dimension. First Hausdorff outer measure, and then Hausdorff dimension. So measure theory is about a certain type of structure, which is this measurable structure or measure theoretical structure. And it is sort of just one notch above having no structure whatsoever. So you have sets. Recall we were talking about these different contexts. You have this category of or context of sets. These are amorphous sets. They don't have any structure whatsoever. You can still talk about cardinality. And then the next step is measurability, basically. And then if you go a little bit further, you get continuity and so on. So let X be a set. Recall that we had this P of X. It was one of these big hyperspaces of subsets. In this case, it was the power set of X. P of X is the collection of all subsets of X. Ultimately, the point of measure theory is to come up with a function on P of X that takes typically real values. So ultimately, want a function that we're going to call measure. So mu is typically the notation, from p of x to, let's say, 0 to infinity, infinity included. So this could be something like the volume of a subset, or the length of a subset, if x is sort of like a one-dimensional thing. And it turns out that the same idea, with certain properties, of course, the same idea is also the foundation of probability theory. So this has two sort of roots. One root is lengths, volumes, and stuff. Area, volumes. And the other side is probability. So somehow, because this notion of a measure sort of generalizes both of these sort of different notions, it turns out to be a very useful tool, because you end up being able to talk about probabilities, and you should think of probabilities as frequencies. The frequency of an event happening, or something happening. Frequencies. Which means that you get to sort of start with a more dynamical question, or a statement if you want, that says something about, oh, you know, the frequency of this happening is this, or something, and you get to interpret that as a sort of area statement, and vice versa. And you should think of it like this, right? So why this is something reasonable. Let's say that I have sort of like this bullseye, and let's say that I'm trying to sort of, I'm an archer, let's say, and I'm trying to sort of hit the target. And you could say something like this. Well, assuming that I am shooting my arrows randomly, the probability that that my arrow is going to hit this region should be proportional to its area, or rather the ratio of the area of the smaller disk to the larger bullseye. Okay. So in principle, it shouldn't matter if sort of the bullseye, the highest point piece is here or here, insofar as the areas are the same. But of course, the probability of hitting different pieces are not what is called uniformly distributed, typically speaking. So there's a bunch of different things happening. And this notion of a probability allows you to sort of talk about these kind of things in a more concrete fashion. So first we need to do certain things. And it turns out that typically you don't want to stick to sort of the power set. It turns out that this is too large in a sense. You want to sort of restrict it. And it turns out the proper structure is what is called a sigma-algebra. So a sigma-algebra on X is a certain collection of subsets of X. That is to say, it's a certain subset of P of X. A sigma-algebra on X is a collection, let's denote it by curly B, satisfying the following properties. So you see, what I'm going to try to do is, I'm going to try to use the algebraic structure that is allowed on this power set. So because you have a collection of subsets to begin with, you can do already a bunch of algebraic operations. That is to say, you can take intersections, you can take unions, and so on, and you can take complements. Such that I need to have three things. So first of all, I want the empty set to be inside my sigma algebra. Second, I want my sigma algebra to be closed under complementation. That is to say, if A is in my sigma algebra, I want its complement to be also in sigma algebra, in the sigma algebra. So this is x take away A, or you can write it like this, A to the C. And third, I want the following. If I take a sequence, countable, infinitely many, sets in the sigma algebra, I want their union to be in the sigma algebra also. These are the three axioms of a sigma algebra. And you should think of this as sort of an algebraic model of standard logic. Okay, there's a bunch of things you can do with this, but ultimately you want to say something like this. A sigma algebra is really the type of events that you deem are sort of measurable. You say something like this. Nothing happening is an event that I allow. That's obviously for algebraic reasons. And I say, if something happens, I want it not happening to be allowed in my system of measurability also. And you're saying that if I allow infinitely many things happening, countably infinitely many things, I want some of them happening as well. So you should think of A, for instance, as the event happens, event A happens. A complement is the event A does not happen. And this union is one of the events A n happens. This is sort of the intuition. And any element in the sigma algebra then is called measurable, or a measurable subset. Any measurable. And a set together with a specified sigma algebra is called a measurable space. Any questions so far? I mean, certainly P of x satisfies these conditions. In other words, P of x itself is a sigma algebra. It is called the discrete sigma algebra. And so when you're first, for instance, studying probability, you're sort of like looking at discrete events. Let's say throwing a die or something like that, or dice. In that case, you take every single event, and that's called the discrete sigma algebra, or discrete probability space, or sorry, the discrete measurable space. So let me give that as an example. So x. For x, let's say a finite set. Finite set. Typically, one takes the measurable structure on x to be x and the power set. And so this is what is called the discrete measurable space. And of course, you don't need to assume that this is finite, actually. It still makes sense. So that's the first example. Another example that is important is, well, if you were to start with x, a metric space, or rather, let's say that you have a set x and you define a metric on it, Okay, the moment you define a metric on a set, you have a notion of open set. And you can look at the smallest sigma algebra that contains all open subsets. And that is what is called the Borel sigma algebra. So be a set, E be a metric, X. So the smallest sigma algebra, which I'm going to denote by B of X, that's sort of the standard notation, at least for me, containing all open subsets relative to D is called the Borel sigma algebra of X. Okay, so when you're talking about metric spaces and when you're talking about the measurability structure of a metric space, typically you're looking into the Borel sigma algebra. And of course, elements of the Borel sigma algebra are called Borel sets or Borel measurable sets and so on. Now, I should mention this. I think I said this a while ago, but let me be more clear. The notion of a sigma algebra codifies Boolean logic. Okay, so this gives so you're allowed to do and, or, and not, ultimately. You can likewise, for instance, given a metric space, you can look at the collection of all open subsets. It turns out that typically the collection of all open subsets is not a sigma algebra, but it's a different structure, which is called a topology. And that turns out to codify what is called intuitionistic logic. And those things are called Heyting algebras. But we're not going to get to that. We're not going to study that. Another interesting thing, for instance, because the Borel sigma algebra of a metric space contains all open subsets, and because it is closed under complementation, the Borel sigma algebra also includes all closed subsets and any countable unions of them and so on. Okay? So you should really think about a Borel measurable subset as a set that you obtain by doing countably many unions or countably many intersections or some combinations of them of some open subsets or closed subsets and so on. Okay. Okay. Any questions so far? Yes.
What was the name of the algebra, the topology?
Borel sigma algebra.
Sorry, the logic structure.
Oh, Heyting algebra.
Thank you.
Yeah. And so this is related to intuitionistic logic. So maybe I should write it like this. Collection of open subsets is what is called a topology. You see, this is one of those instances in math where topology is both the name of a field and the name of a certain structure. Likewise, you see you have an object that is called an algebra. Yes?
Can you elaborate a little bit more on how Boolean logic arises from these axioms?
Yeah, sure. Let me just finish this. Yeah. Okay, so that is from the perspective of a dynamicist, okay? But so if you're a foundations person, probably you're more careful about these kind of things. But basically the idea is the following. Let's say that you have a set X and you're looking at a certain property. And you want to say, oh, you know, this element of X satisfies this property or it doesn't. One of the sort of axioms, foundational axioms, is that given any property, you can build a subset of X. So given property P, satisfied by some elements of X, X in X, such that X has P, has property P, this is a well-defined subset. So you need to assume this. This is, I think, extensionality axiom or something like that. And once you do this, you can say something like, oh, what is the subset that corresponds to the collection of points, X in X, that satisfies property P and Q. Now that corresponds to the intersection of the corresponding subsets and so on. And so if you sort of like follow that route, ultimately you get Boolean algebra there. Or Boolean logic.
Thank you.
Yeah. Yeah, this is interesting, but we're not going to deal too much with that. Okay, so let's talk about measurable dynamics. Okay, so we talked about continuity. In a similar fashion, you define measurability. So recall that one of the characterizations, this was an exercise that I gave, for a function between metric spaces to be continuous is that the preimage of any open set in the target is also open. You do the same thing basically, but with a sigma algebra or with sigma algebras, and that gives you the notion of measurability. For x, y, let's say metric spaces, f from x to y is continuous if and only if for any v t of x, t of y, being the collection of open subsets of y, that is to say the topology of y, the preimage under f is in the topology of x. So this is topology of y. Now, if you have measurable spaces, you define a function to be measurable if the same thing happens, but instead of the topology, you use the sigma algebra. A function f from xb to yc B is a sigma algebra on X, and C is a sigma algebra of Y, on Y, is measurable if for any measurable subset in Y, the preimage is a measurable subset in X. If you have a metric space, here's an exercise, which is nice. If you have metric spaces, then any continuous function between them is also Borel measurable. Borel measurable signifying that I'm endowing both metric spaces with the Borel sigma algebras. Okay, it's a nice exercise. But it is not true that you can always revert this. So exercise, but not vice versa. Or maybe I can give an example which is straightforward. And this is what is called the idea of a characteristic function, or an indicator function if you're doing probability. Or maybe let's be slightly more careful. Let's first look at some examples. For instance, let me let X to be the interval with the standard metric coming from the Euclidean metric. It has a Borel sigma algebra. So I look at all open subsets in the interval, and then I do these operations that generate the Borel sigma algebra, and I look at that collection. Let's look at this. B is going to be a certain subset. Let me look at all the integer points in the interval. So Q intersect 0, 1. I claim that B is a Borel measurable subset. Okay. Well, is it open? Certain and not, because the closure is the whole interval. Is it closed? Well, certain and not, because its complement is not open. The complement is irrationals, and you can approximate any number using irrationals. So it's neither. It's not that straightforward. But now I'm thinking about whether or not I can write B as a bunch of unions or intersections of open subsets. Well, here's one thing I can do. I can say, oh, I know that there are countably many rational numbers inside the integers. That is to say, inside the interval. That is to say, there's a bijection from, let's say, non-negative integers to B. So B it has the same cardinality after all. How many of you are familiar with this idea? So the idea is that you can consider all rational numbers and you can put them in a list. That's sort of the point. And one thing you can sort of like visualize how this can happen is this, right? So to specify a rational number, I need to specify two integers, and then I'm going to look at the ratio. And so let me let Let me look at the integer points in the first quadrant in the plane. Okay. And let's say, for instance, this is 1, 1. This point corresponds to the integer 1. And then let's say this is 2, 1. This corresponds to the integer rational number 2. But then this number, this point corresponds to 1 over 2. Okay. So if I'm trying to see P over Q, this axis is the P axis, this axis is the Q axis. Now, of course, this is overcounting because if this is 1, this is also 1. So really, I'm looking at sort of lines starting at the origin. And so if I'm looking at this, I shouldn't be looking at any other integer point that is sort of covered by the same ray. Okay, so now based on this, I can start counting. Okay, so here is a bijection. I'm not saying this is going to be necessarily explicit, even though you can also come up with explicit bijections like this. Okay, so, oh, by the way, so for instance, what is this point? Because the P value is 0, all of these are zeros. The numerator is 0. And none of these values are defined according to this representation because Q is 0 here. So you don't really think about these things. So you're really looking at this part. Okay, so you can start like this, for instance. There are multiple ways of doing this. Let's start with this. 0, and then I'm going to take this number, and then I'm going to take, oh, I don't go down. I'm going to take this number. Then let's say I'm going to take this number, then this, and stuff. Let me be more clear, perhaps. Recall, I'm looking at P over Q's. That's the P axis, that's the Q axis. That's 0. But this is also 0. So I start here. Then go to this. Then go to this. Now I don't need to go here because I already counted one. So I just skip this piece, and then let's say I go there. And then I don't need to count this because I already counted it. So let's go up, and so on. Okay. So basically, this is sort of the schematic, if you want. By sort of doing the zigzag, I think it is fairly straightforward that I am listing every single integer in a nice fashion. Insofar, of course, if I'm sort of like hitting the same number again, I'm sort of skipping that, but that's not really a matter. Okay, so there's a bijection. Okay, so I have that B equals B sub n for n non-negative. Well, each singleton then, I can write it like this, n. I can write it like this, for instance. Well, you see, each singleton is a closed subset, and I was able to write the rational numbers as a union of countably many closed subsets. By definition, because each of these is inside the Borel sigma-algebra, and because the Borel sigma-algebras are closed under countable unions, this has to be inside. For some reason, I was thinking that it was going to be slightly harder, but like that's one trick. And then another trick you use is you sort of like start with a bunch of points, and then you write the point as the intersection of countably many balls whose radii go to 0. You can do that too. That's one of the common things. But in any event, it's a measurable subset, you see. Any questions about this? It's not closed, it's not open, but it's the next best thing. So this is what is called, it's an F sigma set, if you want. There's a whole field what is called that is called descriptive set theory, that sort of studies different types of sets like this that you can generate when these have like different properties and all that. Okay, so that's one example, and here is an example of a measurable function that is discontinuous, answering this exercise really. So consider this. Same x and same b. No, to x, I guess. Well, I'm going to let f of x equal to 1 if x is in b and 0 otherwise. Okay, so at each integer point, f gives me 1. At each non-integer point, it gives me 0. Okay, this is certainly not a continuous function. There are many discontinuities, but it is measurable. It is Borel measurable. Okay, here's one more exercise. Once I write it down, maybe we should take a break. Basically generalizing this idea, you can really think of functions and sets in a similar fashion. So you should really think of this guy as sort of like a sensor. You're doing certain experiments. Maybe I should write it like this actually, to be more clear. You're doing certain experiments, and then you have a certain sensor or an observable function. And your sensor is really telling whether or not a certain point that you're looking at is hitting this B set that you chose. There's nothing specific about this B set, of course. I was trying to be more concrete. And one has the following. Okay. For any A in the power set, define the characteristic function associated to A. Characteristic function of A by, so if you do sort of abstract math or pure math, you typically use chi sub A, chi for characteristic. If you do probability or more applied stuff, you typically use 1 sub A. Chi sub A or 1 sub A it's a function from x to reals. It really takes two values. Namely, 1 if x is in A and 0 otherwise. Characteristic or indicator. Indicator function. The exercise is that a subset is measurable if and only if the associated characteristic function is measurable relative to the corresponding notions. B is in the sigma algebra if and only if chi sub B is measurable. That's the exercise. Okay. Now, what is the benefit of doing this? Well, the benefit of doing this is the following. Sets, while they're geometric, they're not, perhaps their algebraic properties are not that straightforward. It's not as easy to handle. But if you can interpret every set, any set whatsoever, as a function taking real values, well, you can add functions and you can multiply functions and so on. So doing linear algebraic operations with characteristic functions often turns out to be a lot more easier than using sets themselves. And of course, whenever convenient to sort of go back and forth and stuff. Okay? Let's take a break, and then when we get back, we're going to continue. Okay, I think we're all back. Let's continue. So here is another definition. So you see, this characteristic function construction allows you to sort of come up with measurable functions. But you want to understand the collection of all measurable functions in a sense. And to sort of generalize this idea a little bit, one defines this notion of a simple measurable function. Well, you call a function phi from your space X to R simple measurable if it's a linear combination in the sense of linear algebra of characteristic functions, which means that you have finitely many measurable subsets and finitely many numbers such that phi really is the sum. Okay. And maybe I should leave it as an exercise. Simple measurable functions are indeed measurable. And it turns out that pretty much all measurable functions are basically simple measurable, up to an epsilon, of course. That is to say, any measurable function can be approximated arbitrarily while using simple measurable functions. We're going to discuss that next week, because we're sort of like approaching this theory of integration. But so far, I don't want to go too much into detail about that. I want to give just the basics about measure theory so that we can start talking about how to sort of measure. Any questions? And so if you took linear algebra, this really says that the collection of all simple measurable functions on a measurable space is a vector space. Okay. So now let's try to define this notion of a measure. Maybe first, okay, how should I do this? So there are two notions, okay? One is the notion of a measure, and the other is the notion of an outer measure. And for Hausdorff dimension purposes, really all you need is outer measure, but somehow it is not as nice of an object as the measure itself. So, yeah, let's start with the notion of a measure, so that I can define probability measures and so on. So now we have this notion of a measurable space. A measurable space, recall, is a pair x comma b, where b is a sigma algebra. So once you have a measurable space, now you want to upgrade it to a measure space, or measured space, depending on the area that you're working on. And that's basically a measurable space together with a measure. Not only do you have a notion of which subsets should have a size, but you also have a notion of a size. Be a measurable space a measure on this is a function taking sets as inputs. And for us, the outputs are going to be non-negative numbers, non-negative real numbers, but there are certain variations of this. Mu going from the sigma algebra as the input, and as the output, let's say it's 0 to infinity, infinity included, satisfying the following properties. I need three things. So that this, so mu of b should ultimately correspond to the notion of size. That is to say, mu of b basically should be something like the volume of b. Well, first of all, the empty set should have measure 0. Okay. Second of all, if I have A inside B, well, the larger set should have a larger measure. Let me have a look at my notes. Okay, maybe these axioms are somewhat redundant. But in any event. And the third one is, I want the following. If I have a sequence of measurable subsets, that are disjoint, okay, then the measure of their union should be the sum of the measures. So the mu of the union of an should be equal to the sum of the measures of each piece. Yeah, that's true. Actually, 2 is implied by 3 exercise. So 3 implies 2 here. So you really need 2 assumptions, 1 and 3. Okay. So these are sort of reasonable things to expect a notion of a size should satisfy. So basically the third property really tells you that you can sort of like split, you can start with sort of like a large piece, right? Like let's say, this is a real life example. Let's say that you bought a 2-pound pack of chicken thighs, okay? Like it's 2 pounds. Well, if you cut it in half, the total mass of this plus the total mass of this should add up to 2 pounds. It doesn't matter how you're cutting this. Right? You can chop it up and blah, blah, blah. Insofar as you're not sort of getting rid of pieces, ultimately, it doesn't matter how you're cutting it up. The total mass is going to be the same. It's that simple, really. And this is sort of the mathematical mathematical modeling of the same idea. So typically what you do is, once you have a measure like this, you sort of start to change this target. In particular, if you restrict your image to be the interval 0 to 1, that is called a probability measure. probability measured on X is a measure mu such that the maximum value is 1. So mu of the whole set. X itself has to be inside the Borel sigma algebra because the empty set is in it, and the Borel sigma algebra is closed under complementation. So this capital X is inside. This is 1. Okay. Any questions? Okay. So let's talk about simple examples now. If I were to look at a finite set, okay, with the power set as the Borel sigma, power set as the sigma algebra, which is indeed the Borel sigma algebra relative to the discrete metric, if you think about it. Probability measures on this finite measurable space are really given by what are called probability vectors. Exercise. Let X be a finite set. And let me denote by n the number of things in X. Then the set of probability measures on X is in one-to-one correspondence with the following. Then the set of probability measures on X are in one-to-one correspondence with probability vectors. Probability vectors. Probability vectors. And so these are tuples of real numbers satisfying the following. So P0, P1, Pn minus 1. So that's a vector in Rn. It's an element in Rn such that each entry is non-negative. And they add up to 1. So 0 to n minus 1, pi equals 1. Okay? Now from calculus, we know how to visualize a set like this. And so these subsets in Euclidean spaces are called standard simplices. And so you see, if you're doing dynamics, it turns out to be important to be able to visualize the collection of all probabilities and finding, if possible, a nice probability measure that is somewhat related to your dynamical system. So, standard n-simplex is by definition the collection of all probability vectors in dimension n plus 1. So So if n equals, let's say, 1, all probability vectors in the plane in R2 okay, so if this is 2, then this is 1. So I have pairs, you see, P0 and P1. Both of them are non-negative, and they add up to 1. Okay? So I want P0, P1 in R2. P0 and P1 are both positive or non-negative, and they add up to 1. Well, how do you draw this? Like this. So it's an interval, really. If n equals 2, I have triples now, P0, P1, P2. All of them are non-negative, and they add up to 1. So now it's going to be a piece of a plane, right? So okay, how do you draw this plane? So this really cuts out a plane in R3. Well, what is the normal of this? It is 1, 1, 1, right? So I need to look at the plane passing through the origin, whose normal is 1, 1, 1, and I need to sort of move it around, shift it by 1, so that I get the correct number right on the right-hand side. So I'm not going to be able to draw it properly, but I hope at the very least it's clear that this is going to give me a triangle. This set. And of course, if n equals 3, now I have a tetrahedron and so on. So these are the standard simplices. And you should really think of it like this, right? So let's say that the first axis is P0, and then the second axis is P1. So on this standard n-simplex, each point represents a unique probability measure on my finite set. In this case, I have only 1 point. Sorry, I have 2 points. And so if I were to look at this point, okay, well, this represents, okay, so maybe let's be more specific about this. So example, say X is a set with 2 elements. Let's call the elements H and T. Evocative of a coin, heads and tails. Okay. The Borel sigma, or the sigma-algebra of it, is the power subset, or power set. So which is empty set, heads, tails, and everything. Right? Because X has 2 elements, P of X has to have 4 elements. And so I need to associate to each of these things some number, right? That's the point of a probability measure. Well, I know that mu of the empty set by assumption has to be 0. And because it's a probability measure, I know that mu of X has to be 1. And because this singleton is disjoint from this singleton, well, whatever number I put I give to this guy should be 1 minus this, because if I were to add them up, because of this axiom, the probabilities of each of these events should add up to 1. And so let me call this number, it's going to be a number between 0 and 1, P0, and let me call this number P1. Okay, so you see, now I can think about every single situation like this. Now, if I'm looking at this point, it means that P0 is 1, P1 is 0, which means that even though this is like a probabilistic model, if I'm assuming that this is sort of modeling for me a coin toss, 100% of the time, somehow it is the coin is like tricky. There's it's not fair. 100% of the time, it's going to come heads. Okay, and if I were to look at this middle point, which is exactly when P0 and P1 are equal to 1/2, that means that that's a fair coin. Okay. Any questions about this? I know that this, when you first start studying measure theory and probability theory, it's kind of non-intuitive, but it does take some time, but it is very useful in pretty much in many fields of mathematics and physics and other things. It turns out to be very, very important. And we're going to keep using this. Okay, I think it's a good place to stop for today. On Thursday, we're going to continue. Thank you. Okay, let's start. Good afternoon. So today I want to develop more ideas from measure theory and mention a little bit about entropy, at least in a certain restricted context, because a lot of you are sort of working on problems or final projects that are related. I think it's going to be useful. And I hope to define Hausdorff outer measures rather, and Hausdorff dimension today as well. And if we have time, I want to sort of prove one side of the Moran-Hutchinson formula, which is the upper bound, easier part. So we're sort of like a little behind in terms of the schedule, but not really, because I've sort of shifted the topics around so that instead of covering measure theory next week, we're covering it this week. Okay, so first, some exercises. If I have a measurable space X and B, recall that the measurable space is nothing but a set X with a collection of subsets of X, which is denoted by curly B here. It's supposed to be a sigma-algebra, which means that it has to satisfy certain properties. So if a subset is inside B, its complement should be inside as well. And if you have a bunch of sets in B, you should be able to take the union of them, and that should still be inside B, and so on. So first exercise is this. If I have a mu, a function defined on B, so you see mu is a function whose inputs are sets and outputs are 0 to infinity, infinity included. Mu is a measure, if and only if, all you need is this additivity property or sigma additivity property. For any sequence of pairwise disjoint subsets, the measure of the union should be the sum of the measures, and at least one element should have a finite measure. So monotonicity comes for free, for instance, and the fact that the empty set has measure 0, if you have these two. That's one. Another thing that is sort of interesting is, around what is called monotone convergence. If you have a sequence of subsets that are sort of increasing, so you're taking larger and larger sets, then the measures should converge to the measure of the sort of limit set. And likewise here. If you were to take smaller and smaller sets, the measures should converge to the intersection, so to the measure of the intersection. So these are nice exercises. Okay, any questions about these? Okay, let's keep going. So if I have a measurable space, XB, I'm going to denote by M of xb, the set of all measures, and M sub 1 of xb, the set of all probability measures. Now, next week, once we start talking about invariant measures and stationary measures and all that stuff, so that we can talk about this random process perspective on iterated function systems, instead of using the hyperspace h of x, we're going to use this space of probabilities. And there's going to be, again, an operator acting on this, which is going to be called the Markov operator. Okay? And again, we're going to sort of like go through certain things, and we're going to find it as a unique fixed point and all that stuff. But so far, I'm just introducing this notation. I just want you to think of the collection of probability measures as a set in and of itself. And I'm going to say a couple more words about this in a second. I want to remind you of these simplices and stuff. And here's an exercise. Let x be a set, and let lowercase x be a point. I'm fixing it. And I'm going to I'm going to define a function defined on all subsets, delta sub x, which does the following. Delta sub x of a subset A is 1 if x is in A, 0 otherwise. So in a sense, this is sort of the, it's sort of like a dual of the characteristic function. Recall that last time we associated to any set a certain function, so it's the other way around. So I can write chi sub A of x equals delta sub x of A. Okay, for any A and for any x, this is true. But of course, the emphasis is different. When I'm looking at the characteristic function, I'm thinking of a subset as a function on the set. And when I'm thinking of a delta measure, I'm fixing a point and thinking of it as acting on sets. Ultimately, these two give the same value, but it's slightly different in a sense. And delta sub x for any x is a probability measure on any sigma algebra B on x. And it's called the Dirac delta. Okay? And just to sort of reiterate this idea that instead of the hyperspace, now we're going to have this, so that we can develop this iterated function systems from a probability point of view. Just like in the case of the hyperspace, we could isometrically embed the original space x into the hyperspace. You can do the same thing, and that's essentially done by this delta measure. That is to say, I can think of delta for variable lowercase x as a function from x to the space of probabilities. If, for instance, if x is a metric space, recall that we have a specific sigma algebra, which is called the Borel sigma algebra. It's the smallest sigma algebra on x that contains all open subsets. And so somehow this B, the choice of B is natural, but so far we haven't discussed any notion of convergence. It turns out, of course, that there is a certain metric on the space of probability measures, okay, relative to that, insofar as x is a compact metric space. This space is a complete metric space. In fact, it's a compact metric space. And then this Markov operator that we're going to define, acting on the space of probabilities associated to a BIFS, is going to be a contraction. And then we're going to say, oh, by the Banach contraction principle, there's a unique fixed point here. Okay, this is what's going to happen next week. But so far, I'm just introducing notation. Any questions? Okay. So let's get back to these simplices. Next week, I'm going to define integrability and expectation and these kind of things in a more general context. But I just wanted to introduce these notions when my space is a discrete probability space or discrete measurable space. Because I want to introduce the notion of entropy, at least one version of it. Okay, so let me fix n. Recall that we defined this notion of a standard simplex. So standard n-simplex well, it's going to be a certain subset of vectors. And I'm going to denote it by delta to the n. Okay, so this is a set of all vectors or points in R n plus 1. Wait. Let's do it like this. Okay, maybe this number is wrong right now, but we're going to figure it out. Such that each entry is non-negative, and if I were to add them up, I get 1. Yeah, I think this is correct. So if n were 1, delta to the 1 should be the one-dimensional or one-simplex. And so it's going to be a subset in R2. It's this. That's delta 1. If n is 2, now I'm looking at a subset of R3. And it's going to be this triangle. If n is 3, now I'm looking at the subset in R4. And maybe it's hard to visualize within R4, but this delta 3 is going to be a three-dimensional space. And it's going to be a tetrahedron. It goes on and on. So in a sense, even when, oh, okay, let me remind this as well. Recall, if, let's say, x is, let's start with 0, I guess. Starts from 0, 1, n. So it's if I have a finite set, and I'm taking as a sigma-algebra the whole power set. We discussed last time how any measure, any probability measure on this discrete finite probability space is given by a certain point in the associated simplex. So let me put twiddle here. So that should be delta n. Right? Because if I had 1 point, I can only use one probability. If I have 2 points, I'm going to use delta 1 and so on. Okay, so in general, that means that I can write it like this. Delta to the number of elements in X minus, minus 1. Okay. Okay. So it turns out that for arbitrary measure spaces too, well, let's say maybe for X compact metric space, but more general than a finite set, this is still in a sense true. In other words, it's still useful to think of this guy, the set of probabilities, as a simplex. Now, typically, what's going to happen is that it's going to be an infinite dimensional simplex, but it is still a simplex. And so here is here's sort of like a theorem that is, I believe, a very deep theorem and very beautiful and mysterious. But here's a justification for this idea. Let's first note that for any measurable space, the set of probabilities is going to be closed under affine combinations. Or maybe let's put it like this. For any measurable space XB, for any mu and nu probabilities, and for any, let's say, t between 0 and 1, the interpolation of mu and nu given by t is going to be inside the probability as well. So 1 minus t mu plus t nu is inside this. In other words, the set of probability measures is a convex subset. And so because I'm basically parametrizing the line segment starting from the probability measure mu to the probability measure nu. And I'm saying that line segment is going to be inside the space of, or inside the set of probability measures. I really want you to start thinking about this collection of probabilities as a geometric object. That's sort of what I'm trying to build toward. But you see, when you're calling something a simplex, you're saying something more than saying that it's a convex subset. So let me perhaps write that down as well. Okay, A. Okay. So for instance, if I were to look at one simplex, this line segment, closed, certainly it is convex, right? If I were to take 2 points in it, well, the whole line is going to be inside. And likewise here, I have the triangle, and no matter which 2 points I choose, the whole line is going to be inside the simplex, and likewise here. But something more is true. Because, for instance, in 2 dimensions, I can look at a convex subset like this, the filled-in triangle, or a circle, or a square, and so on. These are all convex subsets, after all. You cannot leave if you're sort of looking at 2 points, and if you were to connect them using a line segment. And of course, maybe I should give an example of a non-convex subset. For instance, this is not convex, because I can leave it using a line. So here's 1 point, here's another point, right? I can, if I were to draw the line between these 2 specific points, I end up needing to leave the set. So these are convex, this is not convex. When you're saying that this is a simplex, really you're sort of specifying, you're distinguishing this from other types of convex subsets. So maybe I should ask you, can you come up with sort of like a property that would help you distinguish the triangle from the circle, let's say, or the square, and so on, among all convex subsets, without specifying the number of edges or something? This is a deep theorem, but like when you think about it, this is in fact true. One thing you can say is the following, okay? If you were to take a triangle, it doesn't matter what the shape of it is. If you were to scale it by some factor and then shift it a little bit, let's say like this, but you should imagine that this triangle it has the same proportions as this triangle, okay? Now the intersection is going to be yet another proportional copy. This is not true for a square, for instance. If you were to take a square, and if you were to shrink it, let's say, by some factor, and shift it around, like this, the intersection, okay, it's still a rectangle, but it's not the square itself. Okay, so perhaps I should give some definitions. Okay. Let me write it like this. A homothety of RD is how should I write it? Is a bijection of the form f of, let's say, x equals cx plus b. Here c is a, let's use a positive number. So I'm scaling the vector, and then I'm adding a certain fixed vector. Okay. Any homothety is a similitude, but not all similitudes are homotheties. So I'm not allowing rotations, for instance. No rotations. And so I can say then, using these triangles, the following. Maybe I should leave that as an exercise then. Let A be a subset in R2. Let's let A to be compact and convex. And convex. Then A is a triangle. If and only if the following happens. And by triangle, I really mean a two-simplex that is not necessarily the standard two-simplex. If and only if, for any two homotheties like that, so for any C1, C2, positive, and for any two vectors B1 and B2, the intersection of the images, so C1 times A plus B1. So I took my shape, scaled it by C1, and then shifted using B1. And then I'm looking at the intersection of this with this guy is one of the three. Either it's empty, right? Because if I were to take the triangle, scale it by some factor, and like move it all the way there, the intersection can be empty. Or maybe I just move it just enough so that the intersection is a point. That can happen as well. Or, well, it's another homothetic image. Or equals to C3A plus B3 for some C3 positive and B3 vector. Okay. So a square and any other shape that you can take that is like reasonable doesn't really satisfy this property. Okay, this is a very nice geometric exercise. And it turns out that in infinite dimensions too, this is true. So really you should think of this space of probabilities as an infinite dimensional triangle, whatever that would mean. Okay. The point of doing that is that even in this infinite dimensional case, the corners end up being important. The corners end up being, for instance, ergodic measures. Yes?
I've got two questions.
Yes.
The first was, we're talking about like mu sub 1 of x comma b as a metric space. Is the metric on it the Dirac delta function, or what's the?
So far we're not using, I didn't say anything that would use the metric.
Okay, but it is a metric space.
Eventually, yes.
Okay, okay. And
Yes.
then the second one is like, how is a homothety different from a affine transformation? Or are they the same?
Well, an affine transformation allows you to do rotations, for instance.
Okay.
Yes. And also, okay, so using sort of linear algebraic notation, you can write it like this. So xd so constant multiple of identity in the linear part. Okay. If you also allowed here rotations, or more generally a product here that is there's an orthogonal matrix, that would give you a similitude. If you say no matter, like I can take any linear transformation whatsoever, that would give you an affine transformation. Yes. Any other questions? So in general too, when you're doing sort of more general dynamics and stuff like that, you look at the space of probability measures, and you want to think of it as something like an infinite dimensional simplex, and you want to figure out the corners, the vertices of it. And those vertices end up being important. That's why I'm sort of pushing for this. Okay, so the general theorem by Choquet. Let B be a what is called a topological vector space. So it's like R2 but infinite dimensional. And A be a subset, compact and convex, and convex. Then A is a simplex, whatever that would mean, if and only if the same thing happens. The same thing. Okay. Really, the example that you should have in mind is this. Any questions so far? Okay, that's okay. Okay, let's talk about a little bit about the expectation or integration on finite measurable spaces. Integration on finite measurable spaces or measure spaces. Finite probability spaces, let's say. Probability space is nothing but a measurable space together with a probability measure specified. Let's say x is 1, 2, ... n. I have n points. And then any probability measure on this is defined by a probability vector. Okay. So each of these i's, pi's, is non-negative, and if I were to add them up, that would give me 1. Now, first exercise. In fact, any function on x taking real values is measurable. Measurable in the sense that we defined last time. Is measurable. Well, what is the sigma algebra I should be using? I should be using the Borel sigma algebra, of course. That is to say, I should be using the smallest sigma algebra defined on the reals that include all open subsets in the reals. Okay? And once you have a measurable subset, once you have a measurable function, you want to define its integral. And depending on what you're doing, you call integral a different thing and denote it differently. Okay? Phi be a function then its integral relative to this probability measure is the following. Then its integral or expectation or average or mean, these are all the same things essentially. Integral, expectation, average or mean relative to mu sub p. Mu sub p, let's denote it to be the probability measure defined by this, is this. So mu equals mu sub p. So mu sub p is, okay, I'm going to write it here. How many of you have seen something like this before? Okay. Well, it's just going to be the following sum. Okay. I from 1 to n, phi of I, so that now I have a real number, but I'm going to weight it using one of these probabilities, one of the associated components. So phi of I, p sub I. That's the definition. And how you denote it can change. And so if you want to write it like an integral, this is how you denote it. Integral on x of phi of x, and then d mu x. This is like a calculus notation if you want. If you're doing probability, you denote it like this. Expectation relative to mu of phi. Another notation that is common is sort of using what is called the bracket notation from physics. And you denote it like this. Mu, phi, and then brackets. It's sort of like an inner product, you want to think of it, perhaps. Okay? So these are all the same things. But somehow, all of these sort of words sort of are associated to different things from a psychological point of view, if at all. Questions?
I was curious about with the measurability of the phi function. Like,
Yes.
I guess, why are we choosing the Borel sigma-algebra for R? Is it just one that we know will work?
Yes. Yeah, that's a standard one. It's like, I mean...
I just don't see like topological stuff happening in X that would make you want to ensure that like open it.
That's true. You could, okay, 2 points. For a general measurable space, you don't really have a topology to think about, but in this case, it's a finite set. And really, the power set of X is the Borel sigma algebra on X relative to the discrete metric. And why is this measurable? Because no matter which subset you choose, the pre-image is going to be measurable, because I'm taking any subset here to be measurable. Yes. Yeah. Okay, any other questions? So you see, given, this is sort of, if you want, you can think of it like a density. And this is sort of some value. You see, you have sort of some, if you want, you can call it a random variable. If you're doing probability, a measurable function is called a random variable. In different fields, you call the same thing different things. And so you have sort of like this random variable, and the expectation really gives you sort of like the best number that summarizes its values. Let's say X is sort of a coin flip. Maybe we should give an example. For instance, consider X to be heads or tails, and phi to be this, and you're betting, okay? You're saying if it's going to come heads, I'm going to give you $100. If it's going to turn out tails, I'm going to give you $500. Okay, that's what you say. So heads equals 100, or maybe let's use 500 minus 500 and minus 5. Plus 1 minus 5, okay? So what I'm saying is that, okay, so we have a coin, but I feel like it's not fair. So you don't know the probability distribution. But you're saying, if it's heads, I'll give you $1. If it's tails, if it comes to tails, you're gonna give me 5 back. And so then you're asking, what is the sort of, how much am I expecting to gain from this? And so this is sort of where the mystery of probability comes into play. Even though something didn't happen, you can sort of like take the average and sort of make sense of it in a sense. And then you say, let's say the probability of heads, let's write it like this, P sub h, let's say that's 3/4, and let's say that the probability of tails is the rest, right? Like, because they have to add up to 1. Let's say that this is sort of the projected probabilities that you're sort of speculating about. And then based on this, you get to sort of look at your expectation. So you need to take this value multiplied by this. 1 times 3 over 4. And then you get to take this value and multiply it by this. Minus 5, 1 over 4. And then this gives you what? 3 minus 5, that's minus 2. So minus 1 over 2. So that means that if these are your bets, and if these are your speculated probabilities, then on average, you're expecting to lose this much dollars, this many dollars. Okay. And of course, if you do statistics, maybe some of this information is known and some of it is unknown. And then in statistics, you have even further sort of procedures that sort of like allow you to sort of optimize one relative to the other one and so on. You can do a bunch of different things. But this is all we need so far. Any questions? Okay. So now let me introduce a specific function associated to a probability measure. And that's going to be called the information function.
Information and the information.
Somewhat related, yes. Okay, so if I have a probability measure, the information function that I'm going to denote by I sub p associated to the probability measure p is the following. So I need to tell what is the value, I need to tell you what is the value of I sub p at input I. Is I sub p of I equals log of 1 over p sub I. Now, why is this defined this way? I don't want to spend too much time. But there is a certain reasoning, let's say, that ultimately ends up justifying why this should be called the information function. So maybe I should say just this, that if this is your expected probabilities, or speculated probabilities, let's say, then this value, so for any fixed I, so the outcome of an event, of an experiment, I sub p of I should be the amount of information gained once you learn that the outcome is I. Okay, maybe I should write it. So this is amount of information gained once one learns that the outcome of an experiment is I. Experiment is I. Or you can say it the other way around as well. You can say I sub p of I is the amount of surprise once I'm told that the outcome is I. Now the expectation of this particular function is called the entropy of p. expectation with respect to itself, of course. In other words, writing it down explicitly, h of p turns out to be this. Pi log of 1 over pi. Okay. Now, many of you are working on results that ultimately use this expression somewhere, and that's why I wanted to give this definition. Now, it turns out that you can sort of like generalize this. There are like things like mutual entropy or conditional entropy and blah, 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 which ultimately all uses this formalism underneath. I don't want to develop that further because we have other things to do, but somehow if you approach entropy as expected amount of gained information, right? But that's the interpretation. If I sub p is telling you the amount of information you should obtain, well, and if entropy is its expectation or its average, h of p really is telling you how much information on average you should be obtaining if you end up learning the outcome of an experiment. Okay? So you should think of this like that. And once you understand this heuristic, it really becomes very useful, even in very abstract contexts. So amount of expected information gain. Okay. Any questions? Yes.
Is the range of the information function like in between 0 to 1? Or
Yeah, I mean you can say it like that too, but yeah. I'm not saying this is an onto function, of course, because it only has finitely many values. Yeah. Any other questions? Now let's try to figure this out then. Let's say that I'm looking at heads or tails. So here n equals 2. And so the space of probabilities is the one-dimensional simplex. So, example. Let's say that x is heads or tails. And I have the probability of heads or probability of tails. Okay. So this is in the one-dimensional simplex here. So let's say that the x-axis is p sub h, and the y-axis is p sub t. Let's try to compute the entropy of this point. So what is h of 1, 0, right? 1, 0 corresponds to this particular point. Now, what does that mean from a probabilistic point of view? Even though you're sort of modeling this heads or tails coin flip, you're saying, I know that with 100% probability it's going to come in heads. Somehow it's very unfair. Now, the amount of surprise should be 0, because you know what's going to happen, which means this should be 0. Okay, let's compute it. So based on the definition, so p sub h log 1 over p sub h plus p sub t log of 1 over p sub t. Okay, this is 0, 0, and that's 1. But here, this is also 1. Log of 1 is 0. Okay, so that's 0. So if you knew what was going to happen, the amount of information gained from doing the experiment would be 0. And again, let's remind ourselves, what is the base of this log, or does it matter? Well, it doesn't matter because changing the base of the log really changes the unit with which you're measuring the amount. If you were to put base 2, the outcome would really be in bits. If you were to use base e, that would be in nats. If you were to use base 10, that would be Hartleys. In applications, of course, this is important, but from an abstract point of view, what unit you use is not important. Okay? Any questions about this? Now, in this situation then, what is the maximum value of entropy that I could achieve? Let's say that I don't know the probabilities. Well, heuristically, it should be right in between. Right? If it's an actually fair coin, the amount of information I'm getting on average should be maximized. And it turns out that that is true. And you can verify this using calculus. For instance, you can use Lagrange multipliers. This is, this is a differentiable function. And so what is the maximum of this? Restricted to the n-simplex. Okay. Lagrange multipliers from multivariable calculus should apply here. So let me just leave that as an exercise, and then we'll take a break. Exercise. So that the probability is like this, Pn. So this is a vector in Rn, which means that it's going to be a point in the n-1 simplex. Then h as a function defined on the n-1 dimensional simplex. Well, let's say like this, is differentiable. Is differentiable. It has a unique maximum point, and its unique max is the barycenter, right, the center of mass, which is 1 over n, 1 over n. And consequently, its maximum value is log n. Some of you are working on things that has this somewhere in the formula. So you're getting the maximum entropy as a value. And in fact, for instance, if you remember the dimension formula for a shift space, we had log of n divided by log of theta. The log of n in the numerator is also the maximum entropy. We haven't defined the probability there, but somehow topology detected the maximum value of entropy. That's also another instantiation of what we called a variational principle. Okay, let's take a break, and then when we come back, we're going to continue. Okay, let's continue. Any other questions? Okay, did this. We have entropy, maximum entropy, that measure. Okay, let's talk about dynamical systems a little bit. Get back to dynamical systems. So, let Xb be a measurable space. And let's let f to be a function from x to itself. We know what it means for f to be measurable. So I'm going to need that. So recall that this means that for any subset in the sigma algebra, its pre-image under F2 is in the sigma algebra. So heuristically, you're saying that if I'm allowing a certain, or if I'm thinking of an event to be a measurable event, well, its measurability shouldn't depend on time. If I can measure it today, I should be able to measure it tomorrow. That's what you're saying. A measure on this space, let's just use a probability measure. Mu, a probability measure, is F invariant if the measure, or rather the probability of an event happening doesn't depend on time. In other words, for any B event admissible, mu of the pre-image, which I'm assuming is inside the sigma algebra, so I can measure it, this is the same thing as mu of B. Okay. Now, if I have a fixed point of F, I can look at the Dirac measure associated to it. Well, that's an invariant measure. And more generally, I can do the following. So you see, just like we did in the case of hyperspaces, we're now sort of encoding the dynamics acting on some space on a different space somehow, but it is easier to handle. So it's more complicated to describe, but it has better properties in a sense. For instance, it is convex, right? If you were to start with an arbitrary ambient space X, you don't know what it looks like. But you know that this space, it's basically a triangle. If X is an X such that f of P of X equals X, that is to say, X is a fixed point of the Pth iterate of F, then for P positive, then let's write it like this. So I'm going to take the average of deltas supported on the orbit. So delta sub x plus delta sub f of x plus delta sub f squared of x delta sub f to the p minus 1 of x. This is not a probability measure. This gives you p. But if I were to divide it by p, now I have a probability measure. Okay. Now, there are many more. It turns out, as an exercise, I should give this as well. Let's look at our standard example. Doubling map. So f of x equals 2x mod 1. Well, the standard integral, or standard measure, which gives you for sort of line segments their lengths, is invariant under F. Then let me just say Lebesgue measure. Okay. And in fact, let's do this as well. exercise for the same doubling map. While the space of invariant Borel invariant measures relative to the Borel sigma algebra is a simplex as well. So the invariant probability measures, so F invariant probability measures is a simplex. Okay, and it turns out that the vertices of the simplex of invariant measures are exactly what are called ergodic measures for F. Later on, in 2 weeks, I think, we're going to study an ergodic theorem that is sort of related to this idea of an ergodicity, of ergodicity as well. But I don't want to define it for now. Okay. Any questions? Okay, let's now define the notion of an outer measure, mention what is called the Carathéodory construction, and then finally define Hausdorff outer measures. Now that we have everything. Now this is sort of like a more abstract point of view. You say, oh, you know, look at this space of probabilities, but you also want to say, how do you actually come up with such a thing? And so this is about like a more constructive approach. So Carathéodory is Greek construction. Barnsley in the book forgets this apostrophe. Even though he's not really discussing this result, he's talking about a different result that I'm not going to mention here. So you start with what is called an outer measure. So let X be a set. An outer measure on X is a function. I'm going to denote it by mu star, star representing that it's not really a measure, but eventually I'm going to drop it. That takes as inputs any subset whatsoever and takes these values. As usual, you can change this later, but for now, let's just leave it like this. Satisfying three things. And again, I'm going to have to look into my notes so that I don't mess it up. Okay. Satisfying. Well, first of all, I want this function to give 0 to empty set. Second, I want this to be monotone. And third, I want subadditivity. So mu of the union, mu of the union of countably many subsets, I want this to be bounded from above by the sum of the measures. Now, what is the difference between a measure and an outer measure? With a measure, if this is a disjoint union, meaning coupled, like no two pieces are disjoint, then you have equality here. With an outer measure, you don't have that. That is to say, with an outer measure, even if this union is disjoint, you might end up overcounting if you were to add up all the individual measures. But the point is that whenever you have an outer measure, Carathéodory tells you a way to construct a measure. So we need a measure based on mu star. Well, for the definition of a measure, I need to define it on a sigma algebra. Even though this power set is a sigma algebra, it turns out that this is too large pretty much all the time. So you need to restrict it. So given an outer measure, we need a notion of measurability relative to this outer measure. And that's related to being able to take a subset and sort of divide it using a measurable subset. Here's what I mean. Let's write it like this. A subset then, once I have an outer measure, I'm going to call it mu star measurable. If for any, let's use T for instance, T for test. So I'm trying to figure out the measurability of A. And the way I figured it out is by testing it using some other subset, some arbitrary subset. For any T, the outer measure of T equals the outer measure of the intersection of T with A plus the outer measure of T take away A. So this is, let's say, A. And you're testing it out. Can I cut it? Can I cut the outer measure into pieces? That's basically what you're trying to do. And you're saying that no matter which set I use to probe, right, this is my test set, subset. What you want is that the outer measure of T, okay, should be the sum of the outer measure of this piece and this piece. So the blue piece is this one, and then the orange piece is this one. Exercise. The collection of mu star measurable subsets turns out to be a sigma algebra. Let's denote it by B sub mu star this is a sigma algebra, meaning empty set is mu star measurable. If A is mu star measurable, its complement 2 is mu star measurable, and so on. And restricted to the sigma algebra, mu star is a measure. So that's, maybe I should leave that. Okay, I'm leaving it as an exercise, but it might take a while. And that's basically the Carathéodory construction. Okay. So basically this means that once you figure out sort of like a reasonable way to associate to any subset whatsoever a certain number, this is like a reasonable, these two are reasonable assumptions. This general construction due to Carathéodory tells you that there is a certain measure associated to it. It says that you cannot use this mu star to measure every single subset whatsoever. You cannot just use the power set. But, you know, there's this other more restricted collection of subsets for which this outer measure gives you a stable sense of size. Yes.
Last time I saw this,
Yes.
I wanted to say that the mu star measurability of a set is like to make it possible to disjointify the sets.
Exactly.
Property 3.
Yes.
But when I was thinking about that, it doesn't look like we're looking at the disjointifiability of A. It looks like we're looking at the disjointifiability
Exactly.
of T.
Yes.
So like, how do those work together?
Well, the point is that you want to be able to, okay, so here's one way to think about this. This is basically like a conditional measure conditioned on A. There's a, so from a probabilistic point of view, you can think of it like that. So you would need to normalize this again, but you're saying if I were to take any event whatsoever in the larger subset, I want to be able to condition the probability of that event happening on whatever set that I'm deeming measurable. Yeah, this is a bizarre thing. It's like somehow you're not using the test set to divide A, but you're using A to divide the test set. Yes. Yes. The fifth time you see this, it's going to start making sense. Okay. Any other questions? I understand this is like maybe a bit too much, and probably we're not going to need all this stuff, but at the very least I wanted you to sort of get exposed to these ideas. Because, you know, typically what ends up happening is that you start seeing this for the first time when you're about to use it, you know, in the middle of a paper, and then you're like, this doesn't make any sense. And it doesn't, but it does in a sense. Okay, so now that we have the notion of an outer measure, we can define Hausdorff outer measures. Okay, Hausdorff outer measure. Hausdorff outer measures and Hausdorff dimension. Dimension. We start with a metric space. And as the sigma algebra, I'm going to choose the Borel sigma algebra. Sigma algebra. Oh, by the way, you know, with this measure theory, there's a bunch more sort of technicalities, completeness of a measure, and blah blah blah. There's a bunch of things, and I'm just like skipping because I think this was sufficient. So what I want is this, okay? I take a subset, an arbitrary subset. So want okay. Define a family of outer measures on X okay. Now there's a bunch of different ways of doing this that are not necessarily equivalent, but we're going to use the most sort of user-friendly version. And really this family is going to be parametrized by non-negative numbers. So h to the s for, so let's write it like this. For s, a non-negative number, and then do the following. Take any subset whatsoever, and then look at its h to the s measure, or outer measure. Now what we're going to do is we're going to start moving the value of s. We're going to vary s. And what we're looking for is a phase transition. What we want is this. For small values of for small values of s, I want the outer measure to give a value infinity. And then for large values of s, I want the outer measure of a to be 0. So it's almost like, it's like you have like water and you're freezing it. And you're lowering the temperature, and at some point, instead of being a liquid, it becomes a solid. I want something like that. I want a phase transition parameter. That phase transition parameter is going to be the dimension. That's what's going to happen. Running out of time, but I think I'll be able to define the outer measure. Okay.
H to the s, is that the name of the family, or is that an element in the family?
It's an element in the family. Let's first fix the parameter s, and let's fix a subset. First, I'm going to take an epsilon as well, and then I'm going to take the epsilon to 0. We find the following. So what I'm going to do is I'm going to cover A using countably many subsets whose diameters are bounded by epsilon. And I'm going to associate to that collection a certain number, which is basically the sum of the diameters to the power s. Okay, so take a sequence of subsets such that the supremum of the diameters is bounded by epsilon. And if I were to take the union, I cover A. So I'm basically overestimating the size of A. We're going to discuss why I would even think about taking the power s. But for now, let's just take it as a definition. And then, of course, I need to optimize. I need to look at the size of the best fitting cover. Okay. Now this s-dimensional outer measure of A is going to be the limit as epsilon goes to 0. Okay, good. I think, so this is going to be the s-dimensional outer Hausdorff measure. We're going to continue working on this next week. Okay, thank you.